So for this example of Euler's method, we'll be using the differential equation y prime is equal to y minus 2 times t with the initial value y of 0 is equal to 1. So we were going to use Euler's method to approximate y of 3/2 using 3 steps. And these steps will be of equal length. So we have y prime is equal to y minus 2t, y of 0 is equal to 1, and our goal is to approximate y of 3/2 using 3 steps of Euler's method. Okay, so to figure out what our horizontal step size should be, which is sometimes called h, but here will be called delta t, we're going to take the final t value, in this case 3/2, subtract the initial t value, 0, and divide it by the number of steps we want to use. So 3/2 minus 0 divided by 3 is going to give us 1/2. So we'll have a step size of 1/2 for this example. Okay, so our initial data, we have t naught is equal to 0 and y naught is equal to 1, as y of 0 is equal to 1. And so we are going to now calculate the derivative at this point using our differential equation. So plugging in t naught and y naught, plugging in 0 for t and 1 for y, we have 1 minus 2 times 0 is equal to 1. So the derivative at this point is going to be equal to 1 given by this differential equation. So we calculate the next y value by taking the previous point and adding the derivative at the previous point times our step size. So in this case, y naught is equal to 1, and our derivative at our previous point is equal to 1, and our step size is equal to 1/2. And so y1 is equal to 1 plus 1 times 1/2. That is 3/2. Okay. So our step size is equal to 1/2, and we are going to be using this general formula. We are going to get our next y value by taking our previous y value and adding the derivative at our previous point and multiplying it by the step size. And we are given that t naught is equal to 0, y naught is equal to 1, and the derivative at our initial point given by this differential equation is equal to 1. So to go to the next t value, we just need to increase our previous t value by our step size. So we'll increase 0 by 1/2 to give us 1/2. And we have previously calculated our next y value to be 3/2. So using these points, we are going to plug them in to our differential equation and find that y prime at 1/2 comma 3/2 is equal to 3/2 minus 2 times 1/2. And 2 times 1/2 is minus 1, and so 3/2 minus 1 is 1/2. And so moving to our next point, t1 is going to be increased by our step size of 1/2, so 1/2 plus 1/2 is 1, so t2 is equal to 1. And to get our next y value, we will plug in our previous y value plus the derivative at our previous point times our step size. And so we can rewrite 3/2 as 6/4, and 1/2 times 1/2 is 1/4. And so this gives us 7/4 as our next y value. Okay, let's clean up this work a little bit. So our point after 1 after two steps, we are now at t is equal to 1 and y is equal to 7/4. So we have one more step to go, and to calculate our next y value, we need the derivative at this point. So we'll plug in 1 and 7/4 into this differential equation. So we'll have 7/4 minus 2 times 1. So y prime of t2, y2 is equal to 7/4 minus 2 times 1. And 2 times 1 is 2, and we can rewrite 2 as 8/4 to give a common denominator. 7/4 minus 8/4 is equal to -1/4. All right, so to get our next t value, we will increase 1 by 1/2, our step size. And we are now at the t value we want to approximate our y value at. So t3 is equal to 3/2. And to calculate y3, we will take our previous point, 7/4, and add our slope at our previous point, -1/4, times our step size, 1/2. And so -1/4 times 1/2 is going to be -1/8. We will rewrite 7/4 as 14/8, multiplying the top and the bottom by 2 to give us a common denominator. And 14/8 minus 1/8 is 13/8. All right, so y of 3/2, since we are now at t is equal to 3/2, is approximately 13/8. So we have our slope field for our differential equation, y prime is equal to y minus 2t. And if we plot the points we've calculated, 0, 1, 1/2, 3/2, I should say 0, 1, 1/2, 3/2, 1, 7/4, and 3/2, 13/8. So we see these points are following the flow of our slope field, though if we used a smaller step size, they would be following much closer. This looks like it is probably overestimating a little bit.